Now let's work on a specific example of regression. So we're going to start with the least square regression, which is going to use this particular equation for computing the optimal parameters, right? So uh, our goal is to actually construct this design matrix first, right? So once we have the design matrix based upon a specific choice of the basis functions, and we're going to use this particular basis function, right? Even though the frequency is going to be adjusted, it's not going to be 1. The base frequency is not going to be 1. Right? The base frequency is going to be 0.5 actually, right? We're going to use a base frequency that's 0.5, and then 1 sine, cosine, this kind of basis, right? And then using this basis, we're going to construct this design matrix, right? And then the optimal theta, which is actually the weights, the optimal weights here for the chosen set of basis functions, can be computed by solving this by doing this particular linear algebra calculation. And we are going to be able to actually discover this very complicated linear algebra calculation is actually encapsulated in a very simple function call, which is called a pseudo inverse using NumPy, right? Using NumPy, and once we have the theta hat, we can make predictions, right? We can make predictions about the shape about this particular function, right? The prediction means that x is not going to be at the locations of the training data, right? X can be arbitrary locations, right? Arbitrary locations. But the design matrix is going to be constructed using the locations of the training data, right? So let's write this code, and during this exercise, many of the calculations are going to become clear, right? So before we do anything, let's import the library we're going to use. Import NumPy as MP, right? And then import matplotlib.pyplot as POT. Right? That's the two libraries. So in order to actually do this exercise, let's try to construct some data. Right? Let's just pretend that we are given a set of data, but in this particular exercise, we're going to construct this fake data inside of this script. Right? It's not going to be realistic data that you can download from my class website, but let's try to construct some fake data. Right? Let's construct fake data, fake training data. Right? It's not a real data that I obtained from somewhere else, but we're just gonna use some fake data. So suppose we have this many 50 training data. Right? And this 50 training data is evenly distributed on the horizontal axis x. So how I'm going to construct this horizontal axis, right? I'm going to use linspace. Linspace is a NumPy function that allows you to generate evenly distributed data on a certain interval. So suppose we want to go from -3 to 3, and then the number of points is just going to be 50, right? If you have used MATLAB before, this linspace function is kind of exactly the same as the MATLAB linspace function. It's going to generate a linearly or evenly distributed data points between this interval from -3 to 3, and with how many points? With this many points, right? And that's going to be our horizontal axis for the training data, right? That's going to be our x. That's going to be our x for the training data. No, xi, I mean, not x, xi. That's going to be the xi of our training data. And then what's going to be the fi, right? What's going to be the fi? What's going to be the corresponding label, right? What's going to be the corresponding label for those training data, right? So let's construct another array first. Let's call it pix, which is just m pi times x, right? So mp.pi is just the the number pi, and then it's a constant, right? Times x, that's gonna give you like a 50. So it's a -3 to it's an evenly distributed array from -3 to 3, and then this array is multiplied with pi, right? And now we can construct our fi. So we're just gonna call it f. F is gonna equal to the sine function pix, and then divided by pix. So if you are used to MATLAB, this division in MATLAB actually means matrix division. It involves some kind of an inverse of the matrix, right? But here in NumPy or in Python, this division is actually component-wise division. Component-wise means what? So pix is an array, right? You're applying this sine function onto every element of that Python array, NumPy array, right? So you're gonna end up with a NumPy array, and this NumPy array is gonna have 50 elements, right? It's actually a one-dimensional array, right? And then pix is also a NumPy array with 50 elements, and then you are gonna do this division component-wise, so element-wise division. So the first element of this NumPy array is gonna divide the first element of this NumPy array, and then the last element of this NumPy array is gonna divide this NumPy array, last element of this NumPy array, and the result is another NumPy array with exactly the same dimension, 50, right? And then we are gonna do a component-wise add. Right, it's add some. So this is gonna be a sinusoidal function. It's gonna have some kind of oscillations, right? But this is gonna be a linear trend, right? It's with a slope of 0.1. So it's gonna give you some kind of slope of that sinusoidal function, right? And then, in addition to that, we're gonna add some random functions, random variations. And this rand n is a random function generator that's inside of this NumPy random library, right? And then this rand n function is going to create a one-dimensional random number array with this many elements, 50, right? And what exactly is rand n, right? Rand n means it's a normal distribution, so it's going to draw random numbers from a normal distribution, right? And this normal distribution has a zero mean, and then the standard deviation is 1, right? So it is possible that you can have random numbers or random numbers that's kind of very close to -1 or 1, right? But we don't want our random number to be so big. We want our random numbers to be smaller as a kind of an additive noise to this kind of a sinusoidal function with a linear trend. Right, so that's why we multiply the random number with 0.05. So it looks like a small noise. It's not like a completely destroying this kind of deterministic part of the function, right? So that's our fake training data. That's our fake training data. So fi is going to be stored inside of this f function, and the xi are going to be stored inside of this x array. Right. So once we have this kind of training data, we can start our training process, right? Let's do our training. So how we are going to do this training? Right? The basic task for the training process is pretty much just first we have to construct this set of basis functions, right? And then the second thing is that we have to solve this particular equation to get the theta hat, right? Once we get the theta hat, then we're done. We're done with our training, because any kind of prediction, the prediction that we can make for arbitrary x can be computed by bringing theta hat into this expression, right? That allows us to do predictions, right? So now let's try to construct our design matrix, right? The design matrix is gonna have what kind of dimension? Let's count, right? So small n is what? Small n is 50. So it's going to have 50 rows, right? But how many columns we're going to have? It's going to have b columns. So b is actually the number of basis functions, right? So depending upon how many basis functions we want to use, B is gonna be different, right? But if we take a look at the functions inside of this particular set, we can see some patterns, right? It's always sine and cosine. For each fixed frequency, you have two functions. One is sine, the other one is cosine, right? And then you increase the frequency, right? And then you have to add the first element, which is actually 1, right? So it's gonna be an even number plus 1. That's an odd number, right? So number of basic functions is gonna be a odd number, right? Odd number, and then depending upon how many monotones you want to have for the fundamental mode, right? Suppose we want to have like so m equals to say 8. We want to have like 8 different modes, right? Then the number of basic function in B is just going to be m times 2, right? M times 2. That's all the sines and cosines, right? And then plus 1, the first one, right? Plus 1. That's gonna be the number of bases that we're gonna have. So it's 2 times 8. That's 16, right? 16 plus 1. That's 17. So our design matrix is gonna have 50 rows and 17 columns, right? So what's gonna be our phi, right? Phi is gonna equal to we're gonna allocate the memory first. Ones. Right. So we're going to generate a phi, which is going to be a matrix. A matrix filled up with ones, right? So every element in this matrix is unity, is 1, right? And then the dimension of this matrix is going to be n rows. It's going to be n rows, and then b columns, right? So it's 50 rows, 17 columns, right? Let's just run this code. Before we run this code, let's make a plot of the training data, right? Let's plot. The training data is going to be x and f. We're going to use blue circles. We're going to use blue circles to actually make a plot, right? Let's just run this code. I have to sort of pick a name for the file. Let's call it E9, the 9th exercise, right? And then let's just run it. So that's the training data. We have 50 points distributed evenly from -3 to 3, and the amplitude, the Fi, is going to have this kind of sinusoidal pattern, right? It's normalized sinusoidal pattern, and then with some kind of linear trend, right? Linear trend, and then we also have some random numbers. That's added onto that deterministic signal as some kind of oscillations, right? That's some kind of a realistic looking fake training there, right? And then what's going to be the dimension of phi, right? The dimension of phi is going to be 50 by 17, right? And and then it's all going to be filled up with ones. So every element inside of this matrix is going to be 1, right? So the first column is going to correspond to the basis function at all the different training data, at the location of all the different training data, x1 to xn. But it's the first basis function. The first basis function is what? The first basis function is actually 1. So the first column of this design matrix is supposed to be 1, right? And that's already fixed, because by default every element inside of this matrix is starting with 1, right? So all we have to do is to actually change the remaining columns of the design matrix. And in order to do that, we are going to use a loop. So we're going to use loop in range. We're going to range over m, right? And then inside of this loop, we are supposed to actually construct all the remaining columns of this design matrix, which is supposed to be sine, cosine, repeat itself, and then with some kind of a multiplicatives of the fundamental frequency, right? So what's gonna be our let me just write this code first. Phi, all the different rows of what column, right? What column? So the first column. So if I write II in range of m, so II is gonna go from 0 to 7, right? But the zeroth column is supposed to be 1, right? 1 is actually fixed, right? So we want to start from the first column, right? The zeroth column is fixed. We want to start from the first column. So it's gonna be different from 0, right? But another thing that we have to pay attention to is actually this kind of a repetition, right? So it always comes with a multiplicity. It's every time, for every iteration, it's going to be 2 functions. It's not like one function, right? It's 2 basis functions instead of like one basic function. So what I'm going to do is that I have to multiply. So if I change my index to, if I compute my index in this particular way, then it's going to give me the index that I want. So when II equal to 0, 0 multiplied 2, that's 0, right? 0 plus 1, that's 1, right? And then the first the zeroth column is 1, and then the first column is going to be a sine function, right? So it's going to np dot sine, right? And what's going to be my fundamental frequency, right? I'm going to use 0.5 times. Again, if I still use II as my index, then it's not going to work because II is all zeros, right? Zeros times 0.5, that's all zeros, right? It's I have to plus 1, right? That's going to be my fundamental frequency, and then I have to multiply with x, right? And that's going to be my that's going to be the sine function. That's going to be the first sine function, right? And the only difference is that I multiply with 0.5 here. It's instead of just 1, right? The reason that I multiply with 0.5 is because of the range. The range of the training data, it's going from like a minus 3 to 3. That's like a minus pi to pi, right? Pi is like 3.5 of them. So I want to have some kind of variations to it. And then the second one, the one that's going to follow it, is going to be a cosine function, right? So phi, right, plus 2. Then it's going to be np dot cosine 0.5 times I plus 1 times x, right? So when II equal to 0, right? 0 times 2, that's 0. Plus 2, that's 2, right? And that's the second column, right? That's the second column. So this is the zeroth column, right? The first column is the sine function that we have already written, and then the second column is going to be the cosine function with the same frequency as the sine function, right? And then let's try it for another II. So if II not equal to 0 anymore, II equals to 1, right? So it's 1 times 2, that's 2. 2 plus 1, that's 3, right? That's the third column. The third column is supposed to be 0, 1, 2, 3. It's supposed to be another sine function, right? The sine function, right? But now the frequency has to be double. So II is no longer 0, right? II is 1 now. 1 plus 1, that's 2. Right? So 2 times 0.5, that's exactly the double of the fundamental frequency, right? And then the one that's following it is 1 times 2 is 2. 2 plus 2, that's 4. The fourth column is another cosine with the frequency doubled, right? So that's going to be my design matrix, and my design matrix is done, right? So here my design matrix is done. And then the next thing that we have to do is to actually use this design matrix to actually solve for theta hat, right? So how are we going to do that? What's going to be this thing, right? What's going to be this thing? We know f. We have f already, right? Small f. Small f is actually given in this particular vector, this particular array, right? So all we have to do is to actually construct the whole thing in the front, right? So how do we actually do that? It's actually quite easy. It's very simple. So all you have to do is to call a function called pseudo inverse, PIMV, and that's gonna give you the whole thing in the front, right? That's called the pseudo inverse. It's a generalized inverse, the generalized inverse of a matrix, right? We know that the inverse function, we have used the inverse function, right? The inverse function is going to work for a square matrix. If the matrix is a square matrix, the number of rows equals to the number of columns, right? But here phi is not. Phi got 50 rows and 17 columns, so the number of rows and columns are not the same. So it's not a square matrix, it's a rectangular matrix. And this, to get the generalized inverse for this rectangular matrix, you have to use a P inverse function, right? And that's going to be the inverse, right? And then all we have to do is to actually multiply this whole thing, the generalized inverse, with F vector, this F array. But we want to do a matrix vector multiplication, right? So we have to do a dot F, right? And the whole thing is called a theta hat, right? The result of this whole calculation is called a theta hat, right? And the theta hat is supposed to have how many elements? It's supposed to have 17 elements, right? Right. Theta hat is supposed to have 17 elements. It's supposed to be equal to the number of basis functions that you have used. The number of basis functions is 17 here, right? So theta hat is supposed to have 17 elements, right? And one element for each basis function, right? So now let's run it. So theta hat, let's see what the theta hat is exactly 17, right? Okay, so now let's try to make some predictions. All right. So how are we going to do predictions, right? Prediction means what? Prediction means that we want to compute this f function for values of x that's not at the location of the training data yet. So let's try to construct suppose we want to make 1,000 predictions, right? And these 1,000 predictions are going to happen on a link space still from -3 to 3, but at locations that's evenly distributed between -3 to 3, right? But with 1,000 samples, right? We're going to make predictions at those locations, right? So how are we going to make this prediction, right? All we have to do is to multiply the theta hat that we have evaluated with the corresponding basis functions, right? But now the basis functions has to be evaluated not at the locations of training data anymore, but at the locations of this big X now, right? So how are we going to do that? Right? Again, we are going to have to sort of come up with a representation of phi, right? Let's just going to call it a capital P. Right? Capital P is going to equal to np dot ones, right? And then the dimension is going to be capital N, right? Capital N. And then how many bases? B bases, right? This many bases, right? And then we are going to have to repeat this particular loop for II in range M, right? But now P 2 times II plus 1 is going to equal to np dot sign 0.5 times II plus 1 times, now it's no longer small x, right? Small x is the locations of the training data, but now we want the locations of the predictions. We want to make predictions at those capital X, right? So now it's capital X here, right? And then P, capital P, 2 times II plus 2 is going to equal to np dot cosine 0.5 times I plus 1 times capital X, right? And that's going to be this phi, this basis matrix evaluated at all the prediction sites, prediction locations, right? And then all we have to do is to do this matrix vector multiplication now, right? So theta hat transpose times this P matrix, right? And this can be done. This can be done by just using this matrix multiplication. So our prediction capital F for all the prediction locations is going to equal to P dot theta hat. Right. It looks like the equation here that I'm typing up is different from theta transpose times phi, right? Maybe you should transpose theta and then do a matrix multiplication with P here, right? But I can tell you, if you have some knowledge about linear algebra, it's gonna give you exactly the same results, right? So if you just move the whole thing over, it's not gonna. It's not you save one operation. You don't have to do the transpose here, right? So that's our prediction. Capital F is going to be our prediction, right? So let's plot our prediction. Let's plot it. Plot dot plot, right? X capital F, and then we are using green solid lines, right? And now let's run it again, right? So that's going to be our prediction. Right, the green solid line is our prediction, and then the blue dots are our training data. Right, so based upon this training data, we have come up with some kind of a solid line that's a fit. Right, that's a fit to all those training data. Right. So that's with those 17 basis functions, right? You can also increase it. Say you can decrease it, right? So suppose let's decrease it to like 6 and see how good the fit actually is, right? Maybe the fit is not as good, but it still looks pretty good, right? It looks still pretty good, right? Or you can increase it. You can increase it, right? Say suppose you increase it to like 10, right? If you increase it to 10, then the fit is going to improve. For example, you're going to be able to actually fit those smaller trends, right? But is that a good thing or a bad thing? Is that a good thing or a bad thing, right? It looks like a good thing, right? Because you can fit the training data more accurately, right? But it could be a bad thing because those small variations might not be the inherent trend of the data, but some just caused by some random noise. If it's random noise, then this kind of small wiggles, the fit to random noise cannot be generalized, right? Which means that your prediction is not necessarily good because you are fitting the data. You are fitting the noise. You are not actually fitting the underlying trend. You are actually fitting the noise, right? So it could be a good thing, could be a bad thing, depending upon the underlying signal and also the characteristics of the noise, right? And later on, if we have time, we're going to talk about different ways of choosing what might be an optimal value for this particular parameter m, right? This parameter m is called a hyperparameter. You have to pick this kind of name, pick this number very carefully, right? Through some operations such as cross-validation, right? And this is a very simple example for least square regression.